Okay, I hope you had a good weekend. I hope you had a good break between calculus and Math 135. I was just digging through some of the other instructors' lecture notes, and I found this Lecture 1 slide from one of the other Math 135 instructors. And it says on one of the pages, it says Math 135 works a bit differently from your other math courses. We do not have traditional lectures. Instead of introducing content, we will focus more on practicing problem solving. You're expected to read ahead, reading assigned at the end of each lecture, and take notes at home. I guess not taking notes during class, but taking notes when you're reading the course notes. In class, you're expected to listen, work through examples and exercises, and share your ideas with the rest of the class. This may not be the easiest of courses. I said that on day one, right? But if you put the time and effort into it, this can definitely be one of the most fun math courses in your first year. Okay, so I was just digging through some of the other Math 135 lectures, and I just found this, and I thought it would be interesting to show this because that instructor's been using this since 2016, and it's been the same slide for 5 years, and I've been doing it a little bit like that. So just in case you thought I was completely weird, other Math 135 instructors are also saying that Math 135 works a bit differently from what you're used to. Instead of introducing content, we're practicing problems and you're reading ahead of time. Okay, so that's just out of just... okay, let's get on with the lecture. Lecture 24. How many of you want assignment tips? Okay, let's do it then. All right, I was not going to show these slides, but then I prepared them anyway. So assignment 4 tips. Question 2. After you applied your unique factorization, you're allowed to use one of the exercises from 6.8 of the course notes to get the D of n formula. So you don't have to come up with the D of n formula out of nowhere. If you did that, that's also okay, as long as you prove it's right. But the D of n formula, you're allowed to use the exercise from section 6.8. You can say by exercise in 6. You have to know which exercise. I'm not going to tell you which one. But if you do that, that's okay. You're asked to prove that that D of n formula is odd if and only if n is a perfect square. How many people got the D of n formula already? Okay, and so if you got the D of n formula and you want to prove that it's odd if and only if n is a perfect square, then think about this. If D of n is odd, can the variables in the D of n formula be odd? So you have your D of n formula. It's like, I don't know, like b1 plus 1 times b2 times some, it's got some variables in it, b1, b2, whatever. Those variables, if D of n is odd, can those variables be odd? Okay, and if you can prove this statement, if D of n is odd if and only if the variables are odd or even or something like that, then you'll get 1 mark for determining the answer to this question right there. Okay, probably 1 mark for your unique factorization, 1 mark for getting the D of n correctly, 1 mark for determining the answer to this question, and then 1 mark for the rest of the proof maybe. That's a sample marking scheme for this question. Okay, for question 3, how many people did 2 different cases? N equals 1 and n bigger than 1. Okay, other people proved it in a different way without splitting it up into these 2 cases? Okay, well if you haven't had a chance to do this yet, I'm just recommending you can do it in 2 different cases, n equals 1 and bigger than 1. All right? Now, if n equals st squared, what does the prime factorization look like? This is not one of the ones where I'm telling you the answer. I'm just asking a question here. If n equals st squared, what does the prime factorization of it look like? Grayson?
The prime factorization of which bit? Because n is an integer, any prime factorization.
Okay, yeah, but what's the so that, yeah, it can have any, okay, so we have n equals p1 a1 times p2 a2 times blah, 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 p n a n. Well, I don't want this n to be the same as that, so I'm going to say n. So that's the prime factorization of n, right? If you didn't know anything about n, then you can write the prime factorization like that. But we know n equals s times t squared. Okay, so what's the prime factorization of st squared look like? Yes, Alina?
You have like the odd, no, the even times, no, No. So it would be something like P1, A1, P2, A2, and then in brackets you have P something times another prime, like Q1. I don't have
Okay, I'm not going to use the A's because those were the ones that I used before, so I'm going to use alphas. And then P, M, alpha M, and then
you bring in another.
another one. Okay, so P1, beta 1,
Yeah.
P2, beta 2, blah, 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 P, M, beta M. Yes, Paige?
Shouldn't there be twos before the betas?
Yeah,
They're
okay.
all squared.
Yeah, the reason for that is because this is equal to S and this is equal to T squared, right? Is that visible? Camera's not in the way, Henry? Jimmy? Okay, good. All right, so if this is T squared, you're going to have prime factorization squared, and the exponents, they just all become doubles, okay? Good, very good. And what happens, I have P1 here, and I also have P1 there. What if P1 is not in the prime factorization of T squared? Then what? Mia? Yeah, then you can just make beta 1 equals 0. So you can, so this should go from 1 to m, this should go from the same thing, 1 to m. Okay, because the same primes are involved in both prime factorizations, it's just that some of the exponents might be 0. Okay, so you have prime factorization here, and then a prime factorization here with exponents that are 2 beta. Oops, whoa, I spent way too long explaining that. The slides started advancing before me. So, what does the prime factorization look like? Good, it looks like that. In a prime factorization, what's a condition on the exponents in order for the number to be square free? So I have a number like this. What do I have to know? What do I know about the exponents in order for it to be square free? Vihang?
Alpha 1 has to be less than A1.
Okay, what if A1 equals 2? Then you have a square in there, okay? What if it equals 3? Then you have a cube. If you have a cube, then you have a square. So, yeah, that's right. So if you write that kind of stuff down, you'll probably get some marks. Question 4. Okay, question 4. It was part A, B, and C, right? They asked you to find a W for 3 different scenarios. For question 4A, you're going to get 1 mark for finding the W and for explaining how you got it. So that's going to be like maybe half a mark for finding the W, half a mark for explaining how you got it. For parts B and C, 1 mark for finding each W and 1 mark for explaining how you got them. Okay? So don't just say, I got the W and I plugged it in and it worked, and so therefore I've proven that this is the W. Technically, you've done what the question asked you to do, but you haven't done what the solution scheme said you're going to be marked on. So someone even asked me about this in the last class. They said, hey, I didn't do that. I did what the question asked me to do. The question asked me to do is prove the W, and I proved the W. And yeah, you did what the question asked you to do, but apparently the solution scheme, after I saw it, I noticed, hey, you're also getting a mark for explaining how you got the W, which isn't technically part of the proof. How you got the W doesn't matter. Like, you're just proving the W is true. You don't have to show how you got it. But according to the marking scheme, you're going to be getting 1 mark for explaining how you got the W. So I just thought I'd let you know that because the question didn't say to do that, but it's in the marking scheme. Okay, so for part A, you can use LDET1. For part B, you can use LDET2. And for part C, you can use parts A and B. Got it? Now, what's so funny now? Everyone's laughing. Oh, what's so funny? Okay. For question 5, use the degree of products formula. That's my recommendation here. And you're going to have 1 mark for setting up the proof by contradiction. Oops, I just told you how to do it. Oops. Okay, so don't use induction, don't use contrapositive. Okay. I guess it's going to be a proof by contradiction. And then you can use the quadratic formula. I hope you saw this on Piazza. A bunch of people asked on Piazza, hey, can I use the quadratic formula? The answer was always yes, yes, yes. So if you didn't see that on Piazza, you're allowed to use the quadratic formula for question 5. Now, if f of x is reducible when f of x equals g of x times h of x, for degree of g of x equals degree of h of x equals 1, sorry, the question is f of x reducible when f of x equals g of x times h of x with degree of g of x and degree of h of x equal to 1? All right? Think about the answer to this question, and if you can write down the answer to that question, you're probably going to get 1 mark for that part at least. Okay, so any other questions about question 5? So those are my assignment tips. How many people have seen Phil, how many people have not seen Phil recording these lectures? Everyone's seen him walking in here with this big tripod and everything? Okay, so at the beginning of the term, well, these were specifically for students that weren't able to come here at the beginning. There's a few of you here now, but at the beginning there's people that had their delays of getting their visas to come to Canada, or they came to Canada and then they had to wait 14 days quarantine before they could come to in-person classes and stuff. So these recordings, we had the Zoom meetings and all that going on so that they could watch the lectures when they couldn't come to class. But now pretty much everyone here is here on campus. And I'm wondering how many people in the class would like these videos to be posted somewhere so that you can review them for the final exam. Okay, you guys all want pretty much, there's some people that are ambivalent, but most people want the videos to be posted somewhere. Okay, then let's do next a vote. What would be most convenient for you to access these lectures? Okay, we can put it on Learn, we can put it on MS Streams, we can put it on YouTube. How many people know Microsoft Streams? Okay, it's like with your UWaterloo account you can get in, but you need 2-factor authentication. And Learn, it's similar, you need the 2-factor authentication. And the videos will probably have to be compressed because the upload limits, okay? You can upload like, I can upload the slides and stuff, but to actually the whole video and everything, it might be a little bit, if you want this chalkboard stuff and stuff. So, and then the other option is YouTube, which is more public, but might be easier to access. So how about we do the vote? How many people MS Streams? How many people want me to put it up on MS Streams? Okay, no one. Learn? A lot of people, okay. And YouTube? Okay, it's about 50. In the other class, it was more YouTube than Learn, and in this class, let's do it again. Learn? Okay, and YouTube? Oh, that's a hard one. It's pretty much 50. But what does it look like?
Whatever's easier for you.
All right, okay. So, okay, good. Now, just to let you know, the videos don't contain any students, okay? The camera is just pointing that way. If by any chance, for some reason, some student comes here, like, okay, I asked you to put the fractional derivative of x or something, we're going to take all that stuff out. That just makes it easiest. And there's not going to be any PII, personally identifiable information. So, example, last names, we're not going to be including any of that. So we're going to take all that stuff out. That's what we're required to do anyway. And anything you want out, that can be removed. It'll take some time, some editing. We'll take that stuff out. If I called your name or something, we'll just take that out. So everyone wants me to put the videos up, but some people might not want certain parts of it, and we'll take that out, okay? Anyone with questions about any of this, don't hesitate to get in touch with me, okay? In the next couple days, I'll answer whatever questions you have about the videos and whatever. So I'll take care of that. Now, don't worry. How many people have read the University of Waterloo privacy policy for recordings of lectures and stuff? Okay, a couple people have. All right. It's pretty big, but you don't have to worry about this part. It says, by engaging in course activities, you are consenting to the use of your appearance, image, voice, text, and chat messaging. Don't worry about all that, because none of your appearance or image or voice or anything that stuff's going to go in the videos anyway. Okay, voice, if you answer a question, your voice, but we're not going to have any personally identifiable information according to the university's guidelines. We're not going to say your last name. Okay, so yeah, so it's, even though it says that by engaging in course activities, you're consenting to the use of your appearance and image and all that, don't worry, because we're not doing it anyway. So you consented to it, but we're not doing it, so don't worry. All right, so I'll try, it's going to take some time before we can put all these videos up online. It's like gigabytes and gigabytes and gigabytes of footage, but we'll work on it, okay? Now, here's a question for the class. Does anyone not know how to find the general solution to a linear Diophantine equation? Okay, I put the slide up because someone came at the end of last class, the Friday class, saying, I need some help on linear Diophantine equations. So no one doesn't know how to find the solutions? You don't know how to find the solutions?
It's just rusty, like I don't know it off the.
It's rusty. Okay, so here's how you find the solutions to a linear Diophantine equation. Okay, you have one solution. You get that from how?
Extended Euclidean.
EA, exactly. Yeah, extended Euclidean algorithm. Once you have x equals x0 and y equals y0, once you have one solution that works, then all of the solutions are the form x equals x0 plus b over the GCD of a and b times any integer n, and y equals y0 minus a over the GCD of a and b times any integer n. Okay, so that's just a formula. Every time you want any solution to a linear Diophantine equation, you just calculate the GCD of the a and b in your ax plus by equals c, and that you get this d, and then you just find one solution from extended Euclidean algorithm, and then you just do x0 plus b over d times n and y0 minus a over d times n. Okay, chapter 7 was only 5 pages long, just 2 simple theorems. One theorem saying like if the GCD has a certain property, then there's a solution to the Diophantine equation. Otherwise, there's not. The other theorem is just this. If you want a general solution, you have one solution, then you just plug it into this formula. Okay, so I'm not exactly sure what, when a student comes and says, I need help with, I need you to explain the course notes part of linear Diophantine equation theorem. I don't know what exactly, if you're specific, I can actually go through more. The proof of this is 1.5 pages long in the course notes. I'm not going to do that during a lecture, but this is the linear Diophantine equation theorem 2. Okay, now this week we're supposed to be doing chapter 8. Okay, this is the week 9 schedule, 8.1, 8.2, 8.3, like that. Some of you might have noticed I tend to start the week N material on the Wednesday of week N. Do you know the reason for that? Each week I'm supposed to be doing 8.1, 8.2, 8.3, but I start that on Wednesdays. Why is that? Because of the assignments, right? The assignment is due on Wednesday, and the assignment is telling you it's saying assessments cover material from weeks 1 to 8, not week 9, and it says don't use the linear Diophantine equation in week 7 assignment, right? And so if I'm teaching you this stuff on Monday, and you have an assignment due on Wednesday, some people haven't even started the assignment until Monday or Tuesday. If I'm teaching you that stuff on Monday, then you're going to get confused. It's like, oh, can I use this modular arithmetic thing? Can I use this GCD theorem when the assignment's only about divisibility? Then it gets confusing, right? So I used Monday to give assignment tips, and then I would start the next chapter like, you got assessed on this, and I taught this, and now it's a new week, you're done the assignment, let's start new stuff, right? I didn't like to overlap things. However, this week it's a bit different, because last week, what was I going to do? I mean, end of chapters, the week 8 was the end of chapter 6, which was just prime factorization. It was, proof that there's an infinite number of primes, Euclid's lemma, and then this stuff, which you already knew. You already knew that when we proved that a cubed divides b cubed implies that a divides b. So it was just some prime factorization stuff. And then chapter 7 really didn't have that much content. It's just like, this is a linear Diophantine equation. It's got a solution if the GCD is like this, and these are all the solutions. And so if you did have questions about something in the course notes, like you don't understand the proof, you have the chance to tell me in advance, to say, I don't understand this, and I can actually maybe go through it in the class. But you can also ask on Piazza. There's 1,300 people that can help you. You can ask during office hours. There's so many opportunities to get help if something in the course notes doesn't make sense to you. Remember, it might not be everyone that wants, you might want more help on certain part of the course notes, but you might be the only one that wants help. Or you and your 15 friends might be the only ones, but there's 80 other students that want me to go on. Okay, so yeah, chapter 6 and chapter 7, I think it wasn't that much anyway, so I figured, okay, I'll start teaching congruences. And the other reason I started chapter 8 early, because what's upcoming now, in week 10, you're going to be doing congruence classes, Fermat's little theorem, the Chinese remainder theorem, splitting a modulus. Okay? How many people know what I'm going to say about these theorems? Anyone can guess?
They aren't fun.
Okay, no, they're fun. They're not too bad. They're not too hard. Individually, everything in this chapter is completely fine, right? It's Chinese remainder theorem. You just read that theorem. It's similar to linear Diophantine equation 2, linear Diophantine equation 1. You read it, it's like these are the general solutions. These are the general solutions. It's just a theorem. It's not that bad. However, now what are you guys talking about over there? You guys are working on your 137 assignment or what? What's going on over there? Oh, okay. No, it was actually people in front of you that were working on something. But okay, I'm just a little bit distracted when I hear all these voices. Okay, I just want to make a point here. Each of these theorems, they're not that hard on their own. Okay, but what's going to be hard? And the reason why I say chapter 8 is going to be the hardest part of the course is that these proofs are going to get complex because you're going to have to know everything, right? You're going to have some problem like prove that this thing divides this GCD of this Diophantine equation using the Chinese remainder theorem for this 3 linear congruences. And then you have to know everything, right? It's like you have to know all of those divisibility theorems, all of the GCD stuff, all of the Diophantine stuff, all of the modular arithmetic stuff, all about congruence classes, Fermat's little theorem, Chinese remainder theorems, and polynomials might be in there. So you're just going to have to know everything and use it all together, and it's going to start getting complicated. And in most of the final exam questions, you probably noticed when you looked at the final exams, you can't do anything because you don't know what this mod is, or you don't know what this congruence class is or something. But then the final exam, everything's like that. You have to use a little bit of everything. So the more practice questions we can do involving all of this, the better, in my opinion. Okay, so that's why congruent stuff I started a little bit early. Okay, now for regrade requests, you've all submitted your regrade requests already if you wanted to. If you disagree with your regrade, how many people submitted a regrade request and didn't get an answer yet? Oh, they still haven't, which question was it for?
Question 4.
Ah, okay. So, oh man, question 4 was the worst. Because that was just if A then B or C. I told you like assignment 3 question 2 is the exact same thing. Just use the same format. Case 1, A implies B. Case 2, A implies not B. And so I don't know why question 4 and question 10 was just a disaster. Okay, a lot of people lost marks when they shouldn't have. If you lost marks on question 4 or question 10 and you didn't get the regrade that you wanted by the end of Tuesday, then let me know. And I have power over all those other graders because you're my students, okay? So I can regrade your midterm. Let me know by the end of Tuesday, though. I don't want like the day before the exam when I have 10 people coming to ask me about questions about other stuff and you want this 0.5 marks back on this midterm. Okay, just let me know by the end of Tuesday. So don't hesitate to ask me about question 10, question 4, and also the induction proof. You might have used a slightly different format from what the TAs wanted, but we gave a format in the class which is based on assignment or exam solutions from previous years. So if you lost marks on the induction because of your induction hypothesis or something, then you can let me know if you actually got it, if you actually did it correctly. Okay, if you did it wrong, then I'm not giving you the marks. Your mark can actually go down. Okay, so regrades, good. Reminder, today there's a Mobius quiz. Wednesday there's an assignment. Now for reading chapters 8.1 to 8.4, pages 122 to 133, that won't take long. I've already covered this material. Okay, I've already covered it. You should still read it because there's gaps. I can't say every single thing in the course notes during the class, but I've covered this material. Now reading 122 to 148, that's worth getting a head start on. Okay, the sooner you get that done, I know it's a lot of work. I know it's demanding. You know, if you don't want to do it, then don't do it. However, I'm just recommending it's worth getting a head start because next chapter, like in order to do practice problems on this stuff, you're going to have to know every theorem. Okay, let's get into some content now. What's the last digit of 7 to the power 3333? Who's lost? Who's like, I don't even know how to start this thing? Okay. How many people think they know how to start this? Good. Okay. Okay, so since there's some people that don't know how to start, I guess it would be not very productive if I just sat here letting everyone else try this. So for those of you that know how to start this, what are you going to do? Vihang?
I think you write down the last digits of 7 to the power 0, to the power 1, to the power 2, and to the power 3. Or 1, 2, 3.
That you could do, but how do you know what the last digit? Because if you can write down the last digit of 7 to the power 0, if you write it in the base 7 representation where you have 7 to the power 0, so is okay. Why did it not leave me any eraser? Okay. So you're thinking of writing 7 to the 3333 as A0 7 to the 0 plus A1 7 to the 1 plus blah blah blah?
No.
What are you doing?
If you, this is what I'm thinking.
Yeah.
If you take the last digits of, say, 7 to the power 1, to the power 2, to the power 3, and to the power 4,
Yeah.
then you can take 333 and then take the remainder of that with 4, or like 7333 modulo 4.
Yeah.
And then whatever you're left with,
Yeah.
you can, that would be in between 0 and 4. And then you just input it into one of the digits. Because the digits keep repeating.
Yeah. Okay, Henry, do you want to try?
That's what I was gonna say, I was just taking it.
Okay, so what's the first, what do we want to do when we want to do 7 to the 3333? We want to get the last digit of it. Paige?
Mod 10 of it?
Mod 10. Okay, what does digit mean? Does anyone know what digit means? Digit originally comes from the Latin word digiti, right? Fingers. And decum is 10. Unfortunately, it's a bit ambiguous because some people like to use the word binary digit to describe bits. Okay, binary digits. I don't like using the word digit when I'm talking about binary. If I'm talking about binary, if I have the number 00110 and I want the third digit of that, I call it the third bit. Okay, because this is binary. And in quantum computing, it would be a quantum bit or qubit. However, some people call those the second and third binary digits. I think that that's just overloading a term. I think digits, when I see the word digit, I assume it's the base 10 digit, okay? Because digit means fingers, decum means 10. Digit is base 10 in my books. But I'm just letting you know, some people in your computer science class, they might talk about binary digits, what I call bits. They call binary digits. So anyway, in the course notes, when they asked what's the last digit of 7 to the 3333, they meant the base 10 digit, okay? So we're going to calculate 7 to the 3333 mod 10. You're explaining the second and third and fourth steps of it, but I'm just asking the first step to get the people that don't know how to start this problem. You're starting to say, okay, we're going to do 7 to the power 1, 7 to the power 2, find one that's similar to a multiple of 10. Okay, that's the procedure. The second and third steps, but this is the first step. So now everyone's got the ball rolling now. You've got, you know what to do. You want to calculate 7 to the 3333 mod 10. Some of you are done. Yeah, Mia?
Why mod 10?
Why mod 10? Because we want the last digit of 7 to the 3333. So digit, they didn't say in the course notes what they meant by digit, so it could have been binary digits or ternary digits or something, but I agree with the course notes. When you see digit, you think base 10. So you mean base 10 digit. Okay, so if you write down 7 to the 3333, it's going to be equal to A0 10 to the 0 plus A1 10 to the 1 plus A2 10 to the 2 plus blah, blah, blah. Do you agree with that? How many people haven't seen that before? I see some people confused. They're like, hey, what? Anyone confused by this? Okay, we learned in earlier in school, if I have like 1, 2, 3, 4, then this is the ones digit, and that's the tens digit, and this is the hundreds digit, this is the thousands digit. The reason for that is because that's 10 to the 0, 1, 10, 100. This is the ones digit. You guys understand what I'm talking about? Now, what's the last digit in the number 7 to the 3333? What is it? What's the last digit? I've written it like that. In terms of A0s and A1s and stuff, what's the last digit? You got it, Mia?
It'll be the remainder divided by.
Yeah, so if I'm only telling you A0, A1, A2, A3, what's the last digit of this number? If I relate it to like the way I was talking about numbers like 4, 5, 6, 7, there's a ones column, a tens column, a hundreds column. You know what I'm talking about? So is that A0 or A1 or what?
Yeah, it'll be
So the last digit is the A0. Okay, now, if I divide, remember the division algorithm? So 7 to the 3333 equals 10 times Q plus R. Here I can factor out the 10, right? So I'm going to have 10. So I have my Q equals, so I have Q equals A1 plus 10 plus, A1 plus A2 10 plus A3 10 to the 10 to the 2 plus A4 10 to the 3. I'm just factoring out the tens from all of those. What am I left with? The remainder. This is 10 to the 0 times 1, right? So this part can't be factored out. So then if I want the remainder, if I want the last digit of 7 to the 3, I want A0. And A0 happens to be the remainder when I divide that by 10 using the division algorithm. Does that all make sense now? Yes. Excellent. Anyone else confused? Good. Okay, so we want this mod 10. Now what's the answer? 7. Okay, good. Powers of 7. What's 7 to the 1? 7 to the 2? 7 to the 3? Did you say 342? 343. 7 to the 4? 2401. 7 to the 5? Okay, there actually was one student in the last class who said 16,000 something, but
16,800? 7?
yeah. Yeah. Okay, so 7, 49, 343, 2401, 16807. 16807 doesn't come up that often, but I think 343 and 2401 come often enough that you see that and you recognize it as a power of 7, right? Okay, so are any of these close to a multiple of 10?
2.01 or
49, 241.
Okay, so 2401 is very close to a multiple of 10 for sure, but it's just as close as 49 is, right? So 49, what's that mod 10? 49 is 9 mod 10, but you could also say minus 1, right? Because, well, you can say 9, and then you can subtract 10 from both sides, and you'll get minus 1. Okay, so 7 squared is congruent to minus 1 mod 10. Now we have 7 to the 3. So, because we know that the square is congruent to minus 1, we can just pull out the largest possible even number out of 3. What's the largest possible even number under 3? 3332, exactly. So we have 7 to the 2 times 1666, that's 3332. So we have 3332 plus 1. That's my exponents. Now, 7 squared is congruent to what mod 10? Minus 1. Minus 1 to the power 2 times 1666? Well, minus 1 to an even number is just equal to 1. So then we just end up with 7 mod 10. So 7 to the 3333 is congruent to 7 mod 10. That means that the last digit of 7 to the 3333 is just 7. Anyone confused? This stuff's easy for you? Okay. Now, some other questions. This is a review for some people. How many people don't know how to check whether or not a number is divisible by 3? Okay, so if I have a number like 96, you don't know whether or not that's divisible by 3. Or you don't know how to check. You don't know an easy, fast way to check that. Okay, that's okay, because I didn't know either when I took Math 135. And some people knew because they just, their high school teacher taught them. But it wasn't really part of the curriculum, right? So, everyone else knows how to check? Tina, your hand is up? You know, you just forgot?
No, I know. So the sum of all the digits add up. If the sum of all the digits is divisible by 3, then the number is divisible by 3.
Perfect. Yeah, so if the sum of all the digits in base 10 is divisible by 3, then you have a number divisible by 3. So this is proposition 8 in chapter 8.3. Okay, a lot of you already knew it. How do you know if a number is divisible by 11? Marissa?
I think you see if the difference between the alternating digit signs is divisible by 11.
Yeah, okay, so this is proposition 9 in chapter 8.3. Check if 11 divides a minus b, where a is the sum of the first digit, third digit, fifth digit, seventh digit, etc. b is the sum of the second digit, fourth digit, sixth digit, eighth digit, etc. Okay, very good and compact way of saying it, by the way. That's even more compact and elegant than the course note says it. And in the last class, someone said something also quite lengthy. Grayson?
First digit means least significant digit.
Oh, yeah. So the first digit here is the 5. Yeah. So what you said is more compact, but what's in the course notes is a little bit more precise, because they say the odd and even digits. But even odd and even digits, do you start on the left or the right? So yeah, so I think what Marissa said is actually the best way of saying it in some sense. So 11 is divided by a minus b, where a is the sum of the first digit, that's the last digit. So I should have actually said last. Oh, I could have said first, third, fifth, seventh, starting from the right. That's what I could have said, right? Okay, but the course notes didn't even say that, so it's just expecting you know. So, okay, does 11 divide this thing right here? Now, I just want to warn you, last class, a bunch of people were using calculators. Who here saw on Piazza someone asked, can we use calculators on the final? Someone asked that on Piazza, you saw that, right? What was the answer? Okay, I didn't know the answer, okay? I really didn't know the answer. I asked the course coordinator, he answered, he said, they're not allowed to use calculators and they won't need one. I don't know what won't need one means, but basically on the assignment you're doing extended Euclidean algorithms for some 4-digit numbers. You have like 6,000 something divided by 5,000 something. It goes in there once and then you have to subtract 2 4-digit numbers. That's all right, okay? If it's not all right, then just practice more without a calculator. So I'm asking now, does 11 divide this number here? This just gives you some practice for checking divisibility of 11, just to make sure you know how to do it if it's on the exam.
It does.
Okay, and so what was your capital A and what was your capital B?
37, 26.
37 and 26. Let me write that on the board if anyone is taking a bit longer. So A equals 37 and B equals 26. Yeah? So what's A minus B? A minus B equals what? 11. And then how do you check if 11 is divisible by 11? You do 1 minus 1, the first digit minus the second digit, you get 0. Is 0 divisible by 11? Okay, so you don't have to do that last step. But here you just do the sum of the first, third, fifth, minus the sum of the second, fourth, sixth, and you end up with 11. 11 is divisible by 11, so the number is divisible by 11. That's proposition 9 of chapter 8.3. Okay, now you remember from Friday. Solve the following system of linear congruencies. How many people remember how to do this? Good. One person remembers. Okay. Some people are okay. A little. That's why I'm reviewing it again. Okay. So how do I start? What's the first step? I want to know an x that satisfies both of these linear congruencies. What's the first thing I can do? Grayson?
Write one as a diagonal equation to definition of modular arithmetic.
Okay, and so what's that Diophantine equation going to be?
Well, you just put it on the screen.
Yeah, I didn't do that. It was just a timer. It just came up. Okay, so x equals 20n plus 12, right? So any number, any integer of the form 20 times an integer plus 12, when you divide it by 20, you're going to get a remainder of 12. Okay? So anyone stuck over here? Anyone wondering like why that is? Or, yeah? Okay. Yeah, so then you've got to review a little bit more for the Wednesday and Friday's lectures. Because that's like when I first defined the modular arithmetic, I said 28 is congruent to 0 mod 7, and 27 is congruent to minus 1 mod 7. Yeah, don't worry. So there's one person that's, so x equals 20n plus 12. If I have 20 times an integer plus 12, then when I divide it by 20, I'll get a remainder of 12. Okay? Now, what's the next thing I do? Yeah, Eric?
Set that congruent to 11 mod 39.
Yes, yeah. So you remember in grade 10 you did systems of linear equations. You have 2 equations, not just one. And so you solve for x in one of the equations, then you plug it into the other equation. Substitution and elimination, you remember those words? All right, well, this is a system of linear congruencies. So I have x is congruent to something. I get a formula for x equals this. And the general solution to the first linear congruence is that x equals this. Then you plug that into the other congruence. And you get this thing, because x equals 20n plus 12, then we're basically, the second question is asking 20n plus 12 is congruent to 11 mod 39. What can I do next? Arnav?
You subtract 12.
Subtract 12 from both sides. Okay, yeah, you remember I did 28 is congruent to 0 mod 7. 27 is congruent to minus 1 mod 7. I subtracted 1 from both sides. So I have 21n is congruent to minus 1 mod 39. Now what am I going to do? Now you want to try? What am I going to do here? It's the same as what I did there.
Okay. Would it be 39n minus 1?
Okay, 39, now I don't want to use the same n.
Okay, m. Then
39y minus 1 equals, yeah, so let's do this systematically. Here we had x is congruent to 12 mod 20. We say the modulus times an integer plus the remainder equals the thing on the left. So the modulus times an integer plus the remainder equals the thing on the left. So here we have the modulus times an integer, which you said correctly, 39 times y, plus the remainder, which is minus 1, equals
the thing on the left.
the thing on the left. So 20n equals 39y minus 1. Everyone's got it? Anyone lagging behind? It's okay. I can go a bit slower. You all okay? Okay. So, I don't know if any hands are up. There's people scratching their head and stuff, but everyone's okay? All right, then let's just rearrange this and we have a linear Diophantine equation. You all know how to solve the linear Diophantine equation? Yeah, okay, extended Euclidean algorithm? Good. Okay, so this is the key point. You have a linear congruence. You want to solve for x. You do the modulus times an integer plus the remainder. That's equal to x. Got it? So let's try this one. 3x is congruent to 5 mod 76. Grayson?
So, could you also change both congruences into equations and then set them equal to each other?
That you could also probably do. Yeah. So instead of doing x equals 20n plus 12, you could have done x equals 39y times, 39y plus 11. You could have done that instead.
Set those two equal together.
That might work, so we could try it. I mean, I think you would get the same Diophantine equation up to a constant, which is absorbed into the x and y, right? I mean, technically, I don't see what's wrong with it, right? You have 39y plus 11 equals x, and you have, and then this also equals 20n plus 12. Yeah, so then, yeah, so that's 39y minus 20n equals -1, which is exactly the same. And those x and y, they can be integers. So you can just let x equal -x prime, and you just relabel the x into a -x, because it can be any integer. You guys all get what I'm saying?
Will we lose marks for using that way?
No, you won't lose marks for that. No, that's a perfectly valid way. Okay, well, he did exactly what we're doing. It's just different order. He just did it in a different order, but it's exactly what we're doing here. Because here we're doing 20n plus 12 equals x. And then here we're doing 39y plus the remainder equals x. And x, because x was equal to 20n plus 12, we ended up with 20n minus 1. So he did the same thing, he just did different order. Nothing wrong with that. Philip?
So just to make sure, the answer to the overall question is just the solutions that you get by applying LDT. So that's
Yeah, it's basically all the values of x that satisfy this system of linear congruencies. You get 10 marks for this on the final. That makes you more confident about the final? You just memorize this procedure and you get 10 marks for that. Okay, so how about 76? So 3x is congruent to 5 mod 76. How are we going to do this? Now, the quicker we get through this, the better. So if anyone wants to volunteer, how do we do this?
Can we do it the same
Yeah, so what's the equation?
3x is equal to 76n plus 5.
Yeah, perfect. Yeah, so, and then you 76, that's exactly what you said, right?
Well,
3x,
I said n instead of y, but yeah.
yeah, 3x equals 76n plus 5. Now, this x and the y, those can be any integer. So if I set n equals negative y, then I have exactly this, right? Does that make sense? People are staring at this like I've spoken Greek or something. Okay, so where's all the chalk now? Oh, all the way over there. Okay, so 76, so you said 3x equals 76n plus 5. Now, if I just let n equal negative y, because this has to work for all integers n.
Yeah.
That means it's also got to work for all integers y. You have negative y. Then you just have the y on that side, right? So, okay. Perfect. So this is just the same as 3x plus 76y equals 5. You're in Diophantine land. Easy. Okay? Now, 3x is congruent to 5 mod 6. Let's do that. The extended Euclidean algorithm doesn't even take that long, right? It's just 3, 5, and 6. So try that one. You done? Okay. What's the answer? Okay, so you get 6y plus 5 equals 3x. GCD of 3 and 6 is 3. 3 doesn't divide 5. So by the linear Diophantine equation theorem 1, there is no solution because the GCD of 3 and 6 doesn't divide 5. Okay? So you can say on the exam there's no solution by LDET1. Also, like, okay, I've gone over the course notes examples, but you're going to have to read it at home to get all the fine details and stuff. There's actually a theorem called linear congruence theorem 1, which is basically saying the same thing as linear Diophantine equation theorem 1. It's basically saying if GCD of 3 and 6 doesn't divide 5, then there's no solutions to this modular congruence. But you can also just derive that from the linear Diophantine equation theorem 1. Okay, but without converting it to a Diophantine equation, you can just look at this and say by the linear congruence theorem, there is no solution. Yeah?
I'm just confused about like what happened to the mod 76.
Oh, okay. All right, so we have 76n plus 5 equals 3x. Are you comfortable with that part? Yeah, okay, so 76n plus 5 equals 3x. Now, this works for any integer n. Do you agree that then it works for any integer y if n equals negative y? Yeah, okay. So then let's plug in negative y into here. We get, where did the chalk go? Okay. Negative y. So this is negative y times that. So this is going to be 3x plus 76y equals 5. Right? And then that's what I have on the board. And then it's a linear Diophantine equation. So you solve that using the extended Euclidean algorithm.
Yes.
Is there any other part? So which, is that okay? Or,
Is this like this is as a question from the next slide?
Yeah. The next slide is 3x is congruent to 5 mod 6.
Yeah.
So in that case, there is a solution, I think. And in this case, I'm trying to show you that sometimes there's no solution. And we find that out by the same procedure, but we find that GCD of 3 and 6 doesn't divide 5. So there's no solutions in this case. Okay, anyone else? Am I going too fast? All right, now, if you have a small modulus, like modulus 10, I want 4x is congruent to 6 mod 10. 10 is a small enough modulus. I don't need to do the extended Euclidean algorithm. I can just do x, what's 5 mod 10? 5. What's 9 mod 10? 9. I don't have to do 11, 12, 13, because 11 is congruent to 1 mod 10. 12 is congruent to 2 mod 10. 13 is congruent to 3 mod 10. And then you're going to learn in the next chapter congruence classes. Okay, so 1, 11, 21, 31. Those are all part of the same congruence class. Okay, the integer is mod 10, or something like that. So we only go up to 9, because if I go to 10, 11, 12, I'm just repeating this all over again. Now, 4x, okay. 4x, 4 times 1, 4 times 2, 4 times 3. What's 4 times 3 mod 10? What's 12 mod 10? 2. Okay, so I have a 2. What's 4 times 4 mod 10? 6. Okay, so I found that by doing this table, just brute force, which is fine on the exam, you can skip the EEA. You just get that when x equals 4 and 9, 4x is congruent to 6 mod 10. Okay? So now try this one. X squared plus x is congruent to 2 mod 8. If you do this the original way where you do 8n plus 2 equals x squared plus x, I guess you'll get a quadratic Diophantine equation. Okay, so, but 8 is a small enough modulus. If you have a modulus that's like under 15, and you're comfortable with doing like the squares of everything up to 15, like 14 squared, 13 squared, 5 times 14, 6 times 14, then as long as the number is small enough that you can manage everything. If it was that 76 example where we had 3x is congruent to 5 mod 76, you probably don't want to do that with a table. But if the modulus is smaller than 15 or so, you can just do it like this. Yeah, and I know it's 4:50, so this is the last example of the class, and anyone that has to go, this is the last example, so you haven't missed anything. Oops. Eric, you don't even have a pen?
I wrote it on his paper.
Oh, okay. You guys are sharing the same pencil?
Well, I have a pencil, but I just decided to write it on his paper.
With his pencil?
Yep.
Okay. So these guys, 2 of them doing it in the same amount of time, but I don't know what to say. So you guys got the answer?
Yeah, and he checked in the textbook and it's right, so.
Oh, okay. Oh, you guys are following along with the textbook now, okay. All right, so how many people think that they know how to do this? How many people think they got the answer? Okay. What's the answer? It's already 4:50, so let's just get the answer now. So, what's the answer? Yeah?
X is 1 or 6.
X is 1 or 6. Very good. Yeah, because when you do this, you only go from 0 to 7. You have x squared from 0 to 7. Now, 6 squared, that's 36. 36 is congruent to what mod 8? 4, because 32 is a multiple of 8. So that's 36 minus 4 is 32. So we have 4 there. Then you do x squared plus x. Another row in the table. You get x squared plus x. When x is equal to 1, we get 1 squared plus 1. That is equal to 1 plus 1, which is 2. 2 is congruent to 2 mod 8. And x equals 6. You have 36 plus 6, which is 42. 42 is 40 plus 2. So it's a multiple of 8 times, a multiple of 8 plus 2. So everyone understands how to solve quadratic congruence equations? Or not equations. Quadratic congruence relations? Okay. Pardon me?
For small ones.
For small moduli, yeah. So here's the course notes. We've done nonlinear congruencies. We've done the example, x squared plus x is congruent to 2 mod 8. The next section of the textbook is 8.6, congruence classes and modular arithmetic. I've already told you congruence classes, you have 11, 21, 31, 41. They're all congruent to 1 mod 10. So You can call those entire things, you can call that a congruence class. So instead of saying let x be an integer, you can say let x be an integer that is congruent to 1 mod 10. So it's a class of numbers, a new class, not just real numbers, rational numbers, complex numbers, whatever. There's also more classes of integers we can create using these congruence classes. So you've done this example, nonlinear congruences. You've done this example, 4x is congruent to 6 mod 10. We did that with a table, right? You've done this example, which was, we got this definition, this proposition 9, how to know if a number is divisible by 11. You did this example. You did whether or not this number is divisible by 11. You did this, how you know something is divisible by 3, proposition 8. We did the last digit of 7 to the power 3333. We did what's 2 to the 22 times 3 to the 33 times 5 to the 555 mod 11. We did that. We did what day of the week is it going to be 3 to the 47 days from now. And so we've done pretty much everything up to this congruence class stuff. Okay? So that's it for today, and I'll see everyone on Wednesday, and anyone that wants to stick around for the office hours, I'll see you here too.